The first 3 slides here are just a recap from last week's, so I'm not going to talk through those, but it's just reminding you of the formula that you need if you're looking at potential dividers. And then 2 examples. I'm not going to talk through those ones. What we want to think about next is what potential dividers are used for. So a potential divider will always be part of a bigger circuit. They're used in a circuit where we want to split the voltage in a particular way to go into another part of the circuit. So you might need a big supply voltage, but something within your circuit might only want a smaller voltage for it to actually work. One of your resistors could be a thermistor or a variable resistor or an LDR, something like that. Basically some kind of variable resistor, because then what happens is the resistance changes of that one, which also then affects the split of the voltage, which then will affect the other part of the circuit. You might also get a transistor, which is basically a fancy automatic switch at the point where the next part of the circuit joins on. So for example, in this one, the LED will only come on when the transistor switches on. Now a transistor only comes on if the potential or the voltage is high enough. So for the voltage to be high enough at that point in the middle of that circuit, that is based on the voltage across the LDR. So it will only come on if the voltage across the LDR is high enough, and that will only happen if the resistance is high, which only happens when it gets dark. So basically that LED comes on automatically when it gets dark enough. So that's the sort of thing it's used for. So what happens, as you can see in that previous slide and in the 2 below, is what you will end up with often is you've got a pair of resistors, and then beside them, connected in parallel, you've got another pair of resistors. And they're then connected, often with a voltmeter in between. Now this is called a Wheatstone bridge, this setup of these 4 resistors. And again, one of them could be, or more than one of them could be a variable resistor or a LDR or whatever. The one on the right is exactly the same as the one on the left. It's drawn in a slightly different way because they've made it into diamond shape, but it is the same. So don't panic if you see it written like that. It is just exactly the same as the one on the left. Okay, it's called a bridge because you've got this bridge that connects the 2 branches, and that will normally have a voltmeter on it. What we then talk about is whether or not this bridge is balanced. And the bridge is balanced when the voltage between A and B is 0, i.e. when the voltmeter reads 0 volts. The voltage between A and B is going to read 0 if the ratio between the 2 resistors on the left is the same as the ratio between the 2 resistors on the right. So if R1 over R2 is equal to R3 over R4, then it is balanced. We've got 0 reading on the voltmeter, and that's because the voltage is split in the same way on both sides. So it might be, say, R2 might be double R1 and R4 might be double R3, for example. So the difference between the voltage at R2 and R4 is 0 because it's split in the same way. For example, so this one here, we have got a 10 volt supply. Or the other thing to mention is you'll see here that the supply voltage is drawn in a slightly different way to what it was earlier on in the circuits and the way you would normally draw a circuit. That's just because it's demonstrating that this is only part of a bigger circuit. So there might be other things connected off the picture that we haven't got. So in this particular example, we've got a 10 volt supply. We've got a pair of resistors on the left that are 6 ohms and 4 ohms, and another pair that are 12 ohms and 8 ohms. And then they're connected by this voltmeter. So if we look at the ratios of these two pairs of resistors, R1 over R2 is 6 over 4, R3 over R4 is 12 over 8. If we simplify those down, they're both 3 over 2. So they're both the same. They're equal. So therefore, the reading on the voltmeter would be 0 volts. If you look at what the voltage actually is on each of those resistors, it would be 6 volts on the 6 ohm one and 4 volts on the 4 ohm one, 6 volts on the 12 and 4 volts on the 8. So the 4 ohm resistor and the 8 ohm resistor both have the same potential. They both have the same voltage, which is measured at A and at B, and so they're both, the difference between them is 0 because they're both the same. What can then happen though is that one of the resistors can change. So resistor 4, for example, in this one, is a variable resistor. So you can have it set up so that it's balanced, read on the voltmeter is 0, but then that's a variable resistor. So that could be altered either manually, or it could have been an LDR that's related to light or whatever. But resistance 4 changes. Now as soon as resistance 4 changes, that then means that your total resistance between R3 and R4 is slightly different. Your ratio of how it's then split, how it's shared between 3 and 4 is slightly different. That's going to also affect your voltage, which now means that the voltage at A is not going to be the same as the voltage at B, so it'll be slightly different. But what the thing to remember though, is that the difference is the same. The difference of the resistance is the same as the difference in the voltage. Okay, so as long as it's only changed by a small amount, then the out of balance potential difference is directly proportional to the difference in the resistance. So here's an example. So RV, which is your variable resistor, the one on the right hand side at the bottom, that is set initially at 320 ohms. And at that point, the bridge is balanced. So the question is asking us, how do we know that the bridge is balanced? And then part B is to calculate the resistance of R, the one above the variable resistor. So we know that it's balanced, so therefore, what is the missing resistance? So there it is again, the question's still there, I just made it a bit smaller. So how do we know that the bridge is balanced? The answer to that is just the bridge is balanced when the voltmeter reads 0 volts. Then it's asking us to calculate the resistance of R. So we know that if it's balanced, that R1 over R2 equals R3 over R4, so then it's just a case of sticking the numbers into that formula, and then from that working out the one that we don't know. So R over 320 equals 600 over 200, 600 over 200 is 3. Rearrange that, which means that R is 3 times 320, which is 960 ohms. So when R is 960, RV is 320, that balances with the other side of the 600 and the 200. The next part of the question then says that the resistance on the variable resistor has changed. So it's been decreased just by 2 ohms. So it's been decreased from 320 to 318 ohms. The voltmeter now reads 3 millivolts. Okay, so by changing the resistance by 2 ohms, what we're doing is we're making it unbalanced by 3 millivolts. So the question is then asking, what's the reading on the voltmeter if we then reduced RV again? So if it was now reduced down to 314 ohms. So we've already talked about the fact that they're directly proportional. So a change of 2 ohms resulted in 3 millivolts on our voltmeter. If we reduce it to 314, that means that we've got a total change of 6 ohms. So if 2 ohms gave us 3 millivolts, then 6 ohms gives us 9 millivolts. Okay, so the reading on the voltmeter would now be 9 millivolts. So it said we're talking about quite small differences. Okay, now, in your notes, I think I mentioned this in the assignment details. I might have been from last week actually. There's a mistake. So I don't know whether or not you've printed off these notes. They are in the file section, so if you've not already looked at them, make sure you've at least had a look at them. I know you don't necessarily all have a printer, and if you don't, then you just have to save it and use it as a digital version just now. But at the bottom of page 7 is this bit. So that's a screenshot taken from page 7 on your notes. There's a section called potential dividers as voltage controllers, and there's a mistake on it. So the 2 resistors on the right hand side that I've drawn the red circles around, they don't match the bit of information that's in green at the bottom. So they need to both be the same. Now it doesn't actually matter what they are because it's all about ratios, it's not about the actual values. So let's just say that they're both 40 ohms. So you could score it off and write it on if you want, or just write a note somewhere to note that that is wrong. Because what the bit in green is then saying, which I've kind of put in red at the bottom as well, the potential at point A on that diagram is the potential across the 80 ohm resistor, the one that should be 80 ohms. So that would be 8 volts, because we've got 10 volts that split 20% to one resistor and 80% to the other, so it'll be 8 volts. The potential at point B would be the potential at this new 40 ohm resistor, and that would be 5 volts. So it says in green the potential at point B is 5 volts. So what that means is that those two resistors must be the same as each other. If the top resistor and the bottom resistor are both 5 volts, then they must also have the same resistance. Okay. So if the potential at A is 8 volts and the potential at B is 5 volts, then the reading on the voltmeter would be 3 volts, because that's the difference between the two. So therefore that Wheatstone bridge is not balanced. Okay. Right. What you're going to be doing is some questions. These ones are actually again from your notes booklet. They're fairly straightforward. So the first lot are just working at the potential difference. So that's just your one pair of resistors, looking at the ratios. 21, so the next question is looking at the two pairs of resistors together and looking at what your ratio is between each lot to say whether or not the voltmeter is going to be, well, basically whether it's balanced or not. So you're going to have 0 volts, and if not, what are you going to have? So you need to work out what the potential is on the left, what the potential is on the right, and the difference between the two is your voltmeter reading. So you're looking at the potential across the bottom resistor in each pair. The difference between the two is your voltmeter reading. Question 22 is the same sort of idea. It's been drawn at 90 degrees to the first one, doesn't matter. So your pair of resistors this time is the 6 and the 9 is one pair, and the 3 and the 6 are the other pair. Okay? And then it's asking you it's basically saying that it's not balanced, and how would you change the values to make it balanced. 23 is the same sort of idea, but this time you're told that it's balanced and you're having to work out the missing resistors, so that's fairly straightforward. You've then got a couple of old past paper questions again. First one, what's meant by a balanced Wheatstone bridge? I covered that earlier on. What then happens if the potential across the battery changes? So think about what that would do as a whole and whether that actually makes any difference or not. And this one I thought was worth mentioning because this is sort of slightly more problem solving-y. So there's a little bit about the ratios between the resistors, and then what we've got is a table that's showing that when the resistance of A and B are changed, what does that do to the voltmeter reading? So if you look at that second row of the table, what that's saying is that if A was 121 ohms and B was 120 ohms, the voltmeter reading is minus 21 millivolts. Now the minus is to do just with which direction the current is flowing, basically. So that's kind of whether the left-hand side is the bigger one or the right-hand side is the bigger one. It's almost just like a vector telling us which way around it goes. So don't worry too much about what that minus means. But so basically if A is bigger than B, you're going to get a negative number, and if B is bigger than A, you'll get a positive number. So what you're looking at is the fact that if you've got 121 ohms at A and 120 ohms at B, i.e. a difference of 1 ohm, that created a voltmeter reading of minus 21 millivolts. So you're just looking at what the difference is between them at each point. So if it's the same difference, it's going to be the same voltmeter reading. But think about whether it's negative or positive. Okay. If the difference is 2 ohms, what's your voltmeter reading now going to be? And if your difference is 0 ohms, what's your voltmeter reading now going to be? And that's all you have to do. Hopefully that makes sense. It shouldn't actually take you too long to do.